Okay, welcome to our video number 3. This time we'll be talking about irrationality of nth roots. And you see that you might wonder why I have on the whiteboard written several times abstract algebra. This is only to make the focus work better. It seems that my camera has a problem when the whiteboard is empty, and this way it should get a little better to have something on the board. I already wrote down the question that we want to answer in this video, namely, why are these three numbers there irrational? How do I know that they are irrational? You might be used to the fact that things like radical 2, radical 3, radical 5 are actually irrational, but radical 4, of course, isn't. Radical 4 is rational, it's just 2. But I'm not sure that everybody has seen the proofs of these facts. Plus, I also want to address higher order roots. So not only square roots, but also cube roots and so on. So let's start with the definition here. So let n be an integer that is greater than 2. And definition. So a positive integer is, so A is a perfect nth power if I can write A as b to the n. For some integer b, and also A is called nth power free if p to the n does not divide A for all primes p. Okay, so the two notions here are perfect nth power and nth power free. You know about perfect squares and you know about square free numbers. This is just a generalization of both of these notions to any power. And I want to make one note here. So note, if A is a positive integer, then I can always write A as b times c, where b is a perfect nth power, and b is nth power free. So let's maybe write down a little example of that. So example, for example, if I'm interested in squares, well, I can just take 8 and I can write it as 2 squared times 2. The first one is a perfect square. The second one is square free. This is a perfect square. And the other one, square free, or another example, I could take 54 and I can write it as 3 cubed times 2. I hope that's right. 27 times 2, that's 54. And now you see this is a perfect cube. While the other factor is cube free. Okay, I could also take, if I do twice that, I will get 108. And that's again 3 cubed times 2 squared. And I still get that the first factor is a perfect cube. And the second factor is cube free. It's not square free, but it just depends what I'm interested in. In the first case, I was interested in squares. In the second and third case, I'm interested in cubes. So this notion can be extended to rational numbers. And just to make it even more comprehensive, I can ask here, I can extend this question to ask, for example, about the cube root of 9 over 7. Right, 9 over 7 is not an integer. So definition, so a positive rational number alpha is called a perfect nth power if when I write alpha as a over b, with a and b being integers, positive integers, b not zero, so positive integers means not zero, positive integers, and the GCD of a and b being 1, then both a and b are perfect nth powers. Yeah, you already know what it means for integers to be perfect nth powers. We just defined that. So you know what it means for a and b to be perfect nth powers. Similarly, you can define what it means to be nth power free for a rational number. And that's also defined in terms of the numerator and denominator. So also alpha is nth power free if p to the n does not divide a and p to the n does not divide b for all primes p. So that's an analog of nth power free for a rational number. So again, let's write just a few examples to illustrate this. So example 9/7, the one we're going to be interested in soon, is actually immediately nth power free. Correction here, yes? But first of all, it shouldn't be B, it should be C. Or C is 1. There's also the option of C being 1 if A itself is perfect nth power. This is already nth power free. What if I take 32 over 15? I can write this as 16 times 2/15. And you see, this 16 is actually a perfect fourth power. while the 2/15 is 4th power free. So what I'm trying to illustrate here is that the same thing that I wrote about the integers, which are now corrected, is also true for rationals. So every positive rational number can be written as a product of a perfect nth power and a rational that is either 1 or nth power free. Yeah, the illustration of that third phenomenon would be if I, for example, take 27/8. Well, that is already a perfect cube. So I can write it as 27/8 times 1. This is a perfect cube. And I wouldn't call 1 cube free because, of course, 1 cube is 1. So the correct statement is every positive rational number can be written as a product of a perfect nth power and a rational that is either nth power free or 1. Okay, so with that terminology developed, we can now actually state our theorem. It's not really a very big theorem, so let's just call it a proposition. That says that. So let n greater than 2 be an integer. Let alpha, a positive rational, not be a perfect nth power. Then there does not exist beta in Q such that beta to the n is alpha. In other words, so one thing to keep in mind is that analysis, real analysis or calculus tells us, but actually you really need analysis to tell you that if I have a positive real number, then its nth root is also a positive real number. So there always exists an nth root inside the real numbers. So this then can be rephrased by saying, oh, if I have alpha, which is not a perfect nth power, then the nth root of alpha is not rational. It is real by this statement in analysis, but it's not rational. So I did not involve any real numbers in the statement of this proposition. It's somehow not necessary to involve them, but if you allow yourself to talk about real numbers and about all their properties, then this is an equivalent statement. Okay. The second thing is you might wonder, well, isn't that just the same, right? I'm already saying that it's not a perfect nth power, so of course it's not an nth power of something. Well, you see, this is not so clear. This is not so obvious even for something as simple as 2. I know that 2 is not a perfect square, which means there is no integer whose square is 2. However, I don't know a priori that there is no rational whose square is 2. The same thing with 9/7. I know there is no integer whose cube is 9, and there's no integer whose cube is 7. So 9/7 is not a perfect cube. But a priori, I don't know if there are no rationals whose cube would give you 9, 7. Because I don't know to start with that somehow the numerator and denominator cannot, I mean, do they really behave separately? That just knowing that 9 is not a perfect cube and 7 is not a perfect cube is enough to say that I cannot have some other numerator and other denominator, the numerator not directly related to 9 and the denominator not directly related to 7, whose cube is 9, 7. The point is no, actually you cannot, but this needs to be shown. So let's see the proof of this proposition. So, proof. Oh, so the first sentence in the proof is something I actually want you to work out on your own. So, it starts with an exercise. Show that it is enough to prove the proposition in the case when alpha is nth power free. So this is what is this exercise asking you to do? It's asking you to do this. Assume I know this proposition in the case when alpha is nth power free. Show then how to prove it when alpha is not a perfect nth power. Okay, so given this exercise, we can now prove the proposition. So we assume alpha is nth power free. So first of all, we write alpha as a over b, with a and b positive integers, with the GCD of a and b being 1. And suppose, to get a contradiction, that beta in Q such that beta to the n is equal to alpha exists. And we write beta similarly to alpha, so C over D, with C and D positive integers, and the GCD of C and D being 1. There are two cases to the proof of this proposition. The first case is when alpha is greater than 1, which is the one I'm going to show you, and the second case is when alpha is equal to 1, which is the case I leave to you. So assume alpha is greater than 1. What's so special about it being greater than 1? When alpha is greater than 1, then it is divisible by some prime. So let P be a prime that divides alpha. Sorry, that divides A. So it's not alpha greater than 1, I'm sorry, it's A greater than 1. So I'm assuming that the numerator of alpha is greater than 1. And then I can definitely find a prime that divides this numerator. Okay, what do we have? Well, we have this. I know that alpha is beta to the n, so A over B is C over D to the n. And clearing the denominators, that gives me A D to the n is equal to B C to the n. But now I have a prime P that divides A, so it also divides this entire left-hand side. But the left-hand side is, of course, equal to the right-hand side. Then I know that P also divides the right-hand side. Okay, but P being a prime, if it divides a product, then it divides one of the factors. But P already divides A. So P cannot divide B because the GCD between A and B is 1. So that means P must divide C to the n. Okay, but then on the other hand, if P divides C to the n, this is again a product of numbers and product of integers, and the prime divides the product if it divides one of the factors. So by induction, we get from this that P divides C. Yeah, if it divides the product, there are 3 C's here, so C times C times C, then P must divide either C or C times C. If it divides C, then you have what you got here already. If P divides C times C, then again it must divide either C or C. So in either case, you always get that P divides C. Oh, but if P divides C, then I know that P to the n divides C to the n. So I started by knowing that P divides this, and now I know that P to the n divides this side. So P to the n must also divide A, D to the n. But what do I know about P? I know that P divides C, and I know that the GCD of C and D is 1, therefore P cannot divide D. So none of these P's here on this side divide D. So that means that all of them have to divide A. So as GCD of CD is 1, we conclude that P to the n divides A. And that's the end of the proof, because that contradicts the assumption that alpha is nth power free. Again, I'm leaving the case A equal to 1 to you. All right, so once we have this proposition, we can now answer all of these questions here. So the answer to these questions, one, 2 is square free. So radical 2 is not rational. In fact, what's important here is not so much that it's square free, is that it's not a perfect square, but being square free implies that. So 12 is not a perfect square. No, it's not square free, right? Because 2 squared divides 12. But it's not a perfect square, so I know that radical 12 is also not rational. Note that radical 12 is equal to 2 radical 3. So this is just another way to prove that radical 3 is not rational. 4 is not a perfect cube. So cube root of 4 is not rational. And finally, 9/7 is not a perfect cube. So cube root of 9/7 is not rational. All of this actually has consequences for irreducibility of polynomials. Why? Because the green is not really working great. If I look at this polynomial, I know that this polynomial is quadratic, so to decide if it's irreducible or not over Q, I can just check if it has roots in Q, and I know its roots are plus and minus radical 2, so I know that they are not in Q. So this implies, so this is irreducible over Q. Same here, x squared minus 12 is irreducible over Q. What about this? Okay, so here I can look at this polynomial. Note that this definitely is a root of that polynomial. But to be able to say if it's irreducible, this polynomial is irreducible over Q or not, I need to know its other roots. And it has 3 roots. One of them is cube root of 4, which I know is not rational by what we just said. What are the other 2? Well, they are the cube root of 4 times zeta 3 and the cube root of 4 times zeta 3 squared, where zeta 3 is cosine 2 pi over 3 plus I sine 2 pi over 3. And because there are these 2 cube roots of unity here, these aren't even real. So in particular, they are not rational. So of course, this is none of these roots are rational. Therefore, this is actually irreducible. So from this I get and finally this polynomial, this element, well, I could look at this polynomial. It's a polynomial that has that root, of course. And what are the roots here? One is the cube root of 9/7, which I just now know it's not rational. What are the other 2? Well, it's the cube root of 9/7 zeta 3 and cube root of 9/7 zeta 3 squared. So again, I know these 2 roots are not even real. So these are not real. So x cubed minus 9/7 is irreducible over